In 1941, America's coal Life-A line depended on hundreds of steel bridges built decades earlier. Millions of tons of wartime freight crossed them daily. If they failed, entire regions would collapse. Then, the Chesapeake and Ohio Railway unveiled the most powerful steam locomotive ever built, a Titan weighing 778,000 pounds, one that exceeded the weight limits of nearly every bridge it touched. More power meant more profit, faster freight, fewer crews, unless it destroyed the very infrastructure it relied on. This is the story of a machine so strong it broke its own world, and why the greatest steam locomotive in history was retired not because it became obsolete, but because it was too powerful to survive. What happens when your greatest achievement becomes your biggest liability? December 7th, 1941. Pearl Harbor did not just pull America into war. It transformed every railroad into a military artery overnight. The Chesapeake and Ohio Railway faced an impossible equation. Its tracks ran through the heart of Appalachia, connecting West Virginia coal fields to Great Lakes steel mills. Coal that fed furnaces. Steel that built tanks, ships, destroyers. The Chesapeake and Ohio was not just moving freight anymore. It was moving the raw materials of survival. But its locomotives were reaching a breaking point. The standard H8 Allegheny could haul 13,000 tons. Impressive for 1940. Not enough for 1942. Wartime demand meant running trains back-to-back, double-heading locomotives, burning through coal and crew wages at rates that made executives wince. Every train that required 2 locomotives instead of 1 meant doubled labor costs, doubled fuel consumption, doubled maintenance. The Chesapeake and Ohio Railway's chief mechanical engineer, a man named William Doremus III, saw a different path, not more locomotives, bigger ones. Lima Locomotive Works received the order in early 1941. Build us something that can replace 2 locomotives with 1. Make it powerful enough to haul 15,000 tons up a 1.14% grade without help. And make it now. What they created would rewrite the limits of steam power. It would expose the fragility hiding beneath every bridge on the line. The H8 Allegheny-class rolled out of Lima's shops in 1941, weighing 389 tons. Not the locomotive weight, just the engine itself. With a fully loaded tender carrying 25 tons of coal and 25,000 gallons of water. The complete machine weighed 778,000 pounds, making it heavy. The numbers were staggering. 67-inch driving wheels, 60-inch diameter boiler, a working pressure of 260 pounds per square inch, and the figure that made engineers catch their breath, 7,600 indicated horsepower. No steam locomotive before or since has matched it. On open track, the Allegheny performed like mechanical poetry, a single locomotive hauling what previously required 2. Replacing double headers with so low runs slashed operating costs by 40%. Crews who had spent careers nursing older engines up mountain grades suddenly had power to spare. Dispatchers could move tonnage faster with fewer locomotives, freeing up motive power for additional trains. The C&O ordered 60 of them between 1941 and 1944. Other railroads watched with envy. The Virginian Railway ordered 8 nearly identical machines. These were not just locomotives. They were the apex of 120 years of steam evolution, the absolute ceiling of what reciprocating steam power could achieve. But there was a problem hiding in those spectacular numbers, one that would not become obvious until bridges started speaking in their own language. The language of cracks. Bridge inspectors noticed it first. Hairline fractures in rivet heads, stress patterns in girders that should not appear for decades, vertical deflection measurements that exceeded design tolerances. The pattern was unmistakable. These formations appeared on bridges after, and only after, Allegheny crossings. Here is what the numbers revealed. The Allegheny's axle load hit 85,280 pounds per driver. Most Chesapeake and Ohio bridges were designed between 1900 and 1915 for locomotives maxing out at 60,000 pounds per axle. The railroad had built their entire infrastructure around locomotives weighing 400,000 to 500,000 pounds. The Allegheny exceeded those limits by 55%. Steel bridges do not fail dramatically at first. They fail slowly, microscopically, through a process called fitting. Every time a heavy load crosses, steel crystals deform slightly. Normally, they recover, but if the load exceeds the design threshold, those deformations become permanent. Microcracks form, they propagate, they connect. After 5 to 10 Allegheny crossings, bridges designed to last 50 years were showing damage that should have taken 30 years of normal traffic to accumulate. The Chesapeake and Ohio's Civil Engineering Department began flagging routes as red. Bridge number 4 over the Greenbrier River was restricted to 10 miles per hour for Allegheny traffic. Bridge number 392, spanning Kanawha Creek, had a temporary weight limit imposed, pending reinforcement. Bridge after bridge after bridge, the very infrastructure that made the Allegheny profitable, was buckling under its weight. Maintenance crews worked around the clock. They welded reinforcement plates. They replaced rivets. They added support columns. They installed heavier girders. They were not maintaining bridges anymore. They were rebuilding them under live traffic in the dark, while the war effort demanded those trains keep running. The question became unavoidable. How much would saving the Allegheny cost? In 1946, with the war over, Chesapeake and Ohio's accounting department ran the numbers nobody wanted to see. Between 1942 and 1956, the railroad spent $12.3 million on emergency bridge reinforcements directly attributable to Allegheny operations. Adjusted for inflation, that is over $200 million in today's dollars. Money that purchased structural steel, engineering consultations, overtime labor, and traffic delays while crews worked. The internal memo was clinical. It said that capital expenditures for infrastructure modification to accommodate H8 class locomotives have exceeded projected operational savings by a factor of 2.7 to 1. Translation: every dollar the Allegheny saved in operating costs cost the railroad nearly $3 in bridge repairs. The cost-benefit analysis got worse. The Allegheny's specialized maintenance requirements, those massive pistons and that extraordinary boiler pressure, demanded skilled labor and expensive parts. The locomotives spent more time in shops than conventional power. Availability rates lagged 15% behind older, lighter designs. And then came the final betrayal. The routes where the Allegheny's power mattered most, steep mountain grades with heavy tonnage, were exactly the routes with the oldest, most vulnerable bridges. The railroad faced an impossible choice: spend millions more rebuilding every bridge to Allegheny standards, or retire the most powerful locomotive ever built. Meanwhile, a different technology was quietly solving the problem. The diesel-electric locomotive did not beat steam because it was more powerful. The EMD F7 diesel produced 1,500 horsepower, 1/5. What an Allegheny could deliver, but 4 F7s, connected in multiple unit operation, could produce 6,000 horsepower while distributing that weight across 32 axles instead of 16. The axle loading was 42,000 pounds, half what the Allegheny demanded. Same pulling power, half the bridge stress. And diesels did not need water towers every 100 miles or massive coaling facilities. In 1956, the Chesapeake and Ohio Railway quietly retired its Allegheny fleet. Not because steam was obsolete, not because its diesel was superior in raw power, but because the infrastructure could not survive what the Allegheny demanded of it. 60 locomotives, representing the absolute pinnacle of steam technology, were cut up for scrap. A few survive in museums. They are static displays of what might have been if American bridges had been built just 20% stronger. The official Chesapeake and Ohio statement blamed dieselization and modernization. The truth was simpler and more profound. They had built a machine too powerful for its own world. The Allegheny locomotive did not fail. It succeeded too completely at the wrong problem. It delivered maximum power when what the railroad needed was compatible power. This pattern repeats across engineering history. Data centers that overwhelm electrical grids, aircraft too large for existing runways, software that demands hardware most users do not possess. Every leap forward carries the same risk, building something magnificent that the supporting infrastructure cannot sustain. The engineers at Lima Locomotive Works created a masterpiece, but masterpieces do not matter if the world they inhabit cannot survive them. 60 years later, the lesson remains. Strength without compatibility is not progress. It is just destruction with better intentions. What are we building today that is too powerful for the world we have?